Welcome to the Deep Dive. Today we're jumping into something really fascinating, the world of quantum computing.
It sounds complex, I know.
Yeah, exactly. That phrase might sound, bit intimidating, like something only scientists and lab coats deal with. But the basic idea, well, it's incredibly powerful. It could potentially change, well, almost everything in ways we're just starting to grasp.
Absolutely.
So, our goal in this deep dive is simple. We want to give you a solid understanding of what quantum computing is all about, even if you're starting from scratch.
Right. We'll cover where it came from, why there's so much buzz around it, where we actually stand today in making it real.
And importantly, how it connects with another huge field, artificial intelligence.
Exactly. So maybe we should start right at the beginning. What is computing?
Good idea. Lay the groundwork.
At its heart, it's basically taking information and processing it to solve problems. Simple as that, really.
Like on your phone or, those massive server farms.
Precisely. They all work by manipulating information using bits. And bits are just like tiny switches, right? They're either on a 1 or off a 0.
The classic binary code.
That's it. Classical computers, even the super powerful ones, they do everything using these simple zeros and ones. They tackle complex problems by breaking them down into, well, incredibly long sequences of these on-off operations.
Okay, so they're obviously incredibly useful. We use them constantly. But where do they hit a wall? What are the limitations?
Well, the problems come when things get really complex. For certain types of calculations, as the problem size grows, the number of steps a classical computer needs just explodes. It's called exponential growth.
Exponential, meaning it gets huge fast.
Unmanageably huge sometimes. Think about trying to simulate exactly how a new drug molecule might interact with proteins in your body, or trying to crack the kind of encryption that protects, say, your online banking.
Okay.
For those kinds of problems, even the fastest supercomputers we have today would need, well, longer than the age of the universe to find the answer. They just run out of road.
Longer than the age of the universe. Wow. That really puts it in perspective. So this is where quantum computing steps in, offering a different path.
Exactly. Quantum computing takes, a pretty radical leap. It uses the rules of quantum mechanics, the physics of the super small atoms and particles.
Okay, quantum mechanics, instead of bits, it uses something else.
It uses qubits. Now, a qubit is fundamentally different. It's not just stuck at 0 or 1.
Not just on or off.
No. Because of a quantum effect called superposition, a qubit can actually be both 0 and 1 at the exact same time.
Both. Simultaneously. How does that work?
Think of it less like a light switch and maybe more like a dimmer switch. It can be fully off, 0, fully on 1, or crucially somewhere in between, representing a combination of both states at once.
The dimmer switch for information. I like that analogy.
Yeah.
Okay, but how does being in multiple states help with computing?
Well, here's where the power comes in. Because each qubit can hold this combination of 0 and 1 if you have, say, n qubits. They can collectively represent 2 to the power of n different states, all simultaneously.
2 to the power of n. Hang on. Classical bits and bits, they just represent n states, right? Or rather, one state out of 2n possibilities at a time.
Exactly. One state at a time for classical.
Right.
But n qubits can represent all 2n states at once. That's an exponential difference.
Wow. Okay, that's a massive jump in information capacity. That's the potential speed up.
That's the core of the potential speed up, yes. And there's another key quantum concept involved, too, called entanglement.
Entanglement. I've heard that term. It sounds weird.
It is weird,
Yeah.
but incredibly powerful. When qubits become entangled, they get linked together in this really deep way. Their fates are intertwined, you could say.
Intertwine how?
If you measure the state of one entangled qubit, say, you find out if it's a 0 or 1, you instantly know the state of the other one. Instantly, no matter how far apart they are.
Miles apart. And you still know instantly.
That's what quantum mechanics tells us. It's like having 2 of those dimmer switches linked. Check one, you know the setting of the other immediately. This connection lets quantum computers perform calculations that are highly coordinated, really parallel, in a way classical computers just can't manage.
Okay, so superposition lets them explore many answers at once, and entanglement links them for coordinated work. That sounds like.
Yeah.
Yeah, the building blocks for some serious computational power. Where did this idea even come from? Was it recent?
Actually, the seeds were planted quite a while back. You have to go back to 1959 to the physicist Richard Feynman.
Feynman, right.
He had this amazing insight. He realized that if we were building computers that operated down at the scale of atoms, well, the weird rules of quantum mechanics would have to come into play.
So he saw it coming way back then.
He did. He even suggested we might be able to use those quantum effects to build totally new, more powerful computers.
Yeah.
Then, fast forward to 1981, he gave a really crucial lecture.
What was the key point?
He argued that classical computers are actually pretty bad at simulating quantum systems because, well, they aren't quantum themselves. He laid out the basic features a quantum computer would need to simulate quantum mechanics properly.
So he kind of designed it conceptually.
In a way, yes, the conceptual framework, but of course, actually building one. Well, that was a whole other challenge. Nobody really knew how back then.
A brilliant idea. But the engineering was a bit daunting.
Immense is probably the word. And it took decades for different approaches to start emerging. It's not like there's just one way to build a quantum computer.
Right. So there are different types. They have heard terms like quantum annealing or gate-based. What are the main flavors?
Yeah, think of them as different kinds of tools for different jobs. One important approach is quantum annealing, or QA.
Okay, annealing. What's that good for?
Imagine you have a really complex problem with tons of possible answers, and you need the absolute best one. An optimization problem.
Like finding the best delivery route or maybe the best investment mix?
Exactly those kinds of things. Quantum annealing uses a quantum process to sort of gently guide the system towards its lowest energy state, which corresponds to that optimal solution. D-Wave is a big company working on this.
So it finds the lowest point in a complex landscape of solutions.
Mm-hmm.
Okay, what about adiabatic quantum computers? AQC. Sounds similar.
It's definitely related. AQC also guides a quantum system. You start with a simple system you understand, where you know the lowest energy state. Then you slowly, adiabatically, means slowly and carefully transform that system into one that represents the complex problem you want to solve.
And if you do it slowly enough,
the system ideally stays in its lowest energy state the whole time. So the final state gives you the answer to your complex problem. It's good for things like satisfiability problems, complex searches.
Okay, so those two are about finding optimal states. What about the gate-based ones? You said that sounds more like classical computers.
In a structural sense, yes. Gate-based quantum computers use sequences of quantum gates. These are like the logic gates A and D or R, not in your laptop, but they operate on qubits.
Quantum logic gates.
Right. They perform specific quantum operations. You have single qubit gates that manipulate one qubit superposition, change its dimmer setting if you like. And then you have multi-qubit gates, which are crucial because they create entanglement between qubits. They link them together.
So you build up calculations step by step, like a circuit diagram, but using these quantum operations.
That's the idea. These gate operations are described mathematically by something called unitary matrices, which basically ensures the quantum probabilities are preserved. And importantly, theory tells us you don't need millions of different gates. A small, universal set of basic gates can be combined to build up pretty much any quantum computation you can imagine.
Universal gates. That sounds really flexible, yeah. Very powerful. Any other major approaches out there?
There's another interesting one called boson sampling. It's a bit more specialized. It uses photons, particles of light.
Light particles.
Yeah. You send photons through a network of optical components, like beam splitters. Then you look at the pattern of photons coming out. Analyzing that pattern lets you perform specific calculations that are thought to be incredibly hard for classical computers.
Fascinating. Using light itself for computation.
Mm-hmm.
Okay, so we have these different ways to potentially build quantum computers. Let's get back to the why. Why is this such a huge deal? What could they do?
The potential impact is, well, it's hard to overstate. They promise to solve problems that are just completely intractable today, impossible for even the biggest supercomputers.
Okay, like what? Give us some concrete examples.
Well, a big one is cryptography, security.
How so?
Much of the encryption we rely on daily for secure websites, banking, communications, it depends on mathematical problems being incredibly hard for classical computers to solve, factoring large numbers, for instance.
Right, that's what makes RSA encryption work, isn't it?
Exactly. But a powerful enough quantum computer running the right quantum algorithm could potentially break that kind of encryption relatively easily.
Uh-oh. That sounds bad.
It's a serious concern, which is why there's a huge global effort now to develop new encryption methods that are quantum resistant, immune to attacks from both classical and quantum computers.
Okay, so cybersecurity is a major area. What else?
Material science, drug discovery. These are potentially revolutionary areas. Simulating how molecules behave, how materials work at the quantum level that's incredibly demanding classically.
Because molecules are quantum systems.
Precisely. Quantum computers could let us design entirely new materials from the ground up with exactly the properties we want. They can let us simulate how potential drugs interact with targets in the body with incredible accuracy, dramatically speeding up the discovery of new medicines.
Predicting protein folding, maybe.
That's a classic example. Or designing better catalysts for chemical reactions, developing much more efficient batteries by modeling the chemistry inside them accurately.
So new materials, better drugs, cleaner energy. The scope seems enormous.
It really is. And think about finance, more sophisticated risk modeling, optimizing complex portfolios, maybe much faster fraud detection, or logistics solving incredibly hard scheduling problems like optimizing traffic flow or manufacturing processes, even things like fluid dynamics for designing better airplanes or cars.
Okay, it seems like almost any field involving complex systems or optimization could be impacted. So the big question, where are we now? Are these things in data centers ready to go?
Not quite yet. We've seen amazing progress, truly remarkable. But the quantum computers we have today, well, they're still quite limited.
Limited how? Number of qubits.
That's a big part of it. They have a relatively small number of what you might call useful qubits, nothing like the trillions of bits in a classical supercomputer.
Okay, so scale is still a major challenge.
Definitely. You hear talk about quantum supremacy or quantum advantage. That's the milestone where a quantum computer demonstrably does anything that a classical computer practically can't, even if the task itself isn't immediately useful.
Has that happened?
There have been claims and demonstrations on very specific, often quite artificial problems. It shows the potential, but it's not like they're solving real-world problems broadly yet.
So what are today's machines like?
We're currently in what's often called the NISQ era, noisy intermediate scale quantum.
Noisy, as in they make mistakes.
Exactly. Quantum states are incredibly fragile. They're easily disturbed by tiny vibrations, stray electromagnetic fields, even just interacting with their environment. This is called decoherence, and it causes errors in the calculation.
The qubits lose their quantumness.
Sort of, yes. Plus, the quantum gates themselves aren't perfect. There can be errors in setting up the qubits initially, and errors when we try to read out the final answer.
And correcting these errors isn't easy.
It's much harder than in classical computers. There's a fundamental rule in quantum mechanics, the no-cloning theorem, which says you can't just make perfect copies of an unknown quantum state. That makes standard error correction techniques, which rely on redundancy and copying, really difficult to apply directly.
Wow, okay. So noise and error correction are huge hurdles.
They are the major challenges right now, but people are working incredibly hard on them. For these current NISQ machines, there are techniques called quantum error mitigation, or QEM.
Mitigation, not correction.
Right. Mitigation means trying to reduce the impact of the noise rather than eliminating it completely. It involves clever tricks like running the calculation many times in slightly different ways, and then using classical processing to try and estimate what the correct noise-free answer would have been.
Sort of averaging out the noise.
In a sophisticated way, yes. It's a practical approach for the near term.
And the longer-term solution, is it error correction?
That's the ultimate goal. The idea is to create logical qubits. You take many physical noisy qubits and encode the information across them in a very clever, redundant way.
Like a team of unreliable workers producing reliable work together.
That's a decent analogy. This collective encoding makes the logical qubit much more robust against errors affecting individual physical qubits. Developing effective quantum error correction codes and building systems with enough physical qubits to implement them, that's where a lot of the effort is focused for future fault-tolerant machines.
Logical qubits. Okay. Now, you mentioned there are different ways people are trying to build the physical qubits themselves. Can you give us a quick tour of the main technologies?
Sure. It's quite a zoo out there. Different groups are betting on different physical systems. One major approach uses superconducting circuits. These are tiny electrical circuits made from superconducting materials, cooled down to near absolute zero. Companies like IBM and Google use these.
Super cold circuits. What else?
Then you have trapped ions. Here, scientists use electric and magnetic fields to trap individual charged atoms, ions, in vacuum chambers. They use lasers to manipulate the quantum states of these ions. They're known for being very precise, high fidelity.
Trapping single atoms.
Yes.
Amazing. More.
Neutral atoms are another approach. Similar idea, but using uncharged atoms held in place by laser beams like optical tweezers. Quera computing is a notable player here. Then there's silicon spin qubits.
like in normal computer chips.
Exactly. The idea is to use the quantum property of electrons called spin while they're inside silicon. The big hope here is that maybe we can leverage the massive existing infrastructure and know-how of the semiconductor industry to scale these up. Intel and Quetech are working on this.
That could be huge for manufacturing.
It could be. Then there are photonic qubits using single particles of light, photons. These are interesting because light travels easily, so they might be good for connecting quantum computers together in networks.
Quantum internet, maybe?
Potentially, yes. And there are more exotic approaches, too. Topological qubits, which Microsoft is heavily invested in, aim to encode information in the shape or topology of the quantum system, which could make them naturally resistant to noise. It's theoretically very appealing, but proving quite challenging to build.
Wow. Any others, just briefly?
Oh, sure. There are NMR qubits using nuclear magnetic resonance, flux qubits like D-wave uses for annealing, specialized bosonic qubits designed to be more noise resilient, continuous variable qubits. It's a really active area of research. People are trying many different angles.
It really sounds like a race, exploring all these different physical platforms.
It is. And alongside the hardware, you need the software. We have things like quantum emulators, classical software that mimics small quantum computers, super useful for testing algorithms, and resource estimators that help figure out how many qubits and gates you'd actually need for a specific problem on a future machine.
So the software side is just as important. Programming languages for quantum computers.
Absolutely critical. Developing quantum programming languages, compilers, operating systems.
Yeah.
The whole software stack is being built up, trying to make it possible for people who aren't quantum physicists to actually use these machines eventually.
Right. Abstracting away the complexity. Still, it sounds like there's debate about whether we'll ever get to truly large universal machines.
There is some healthy skepticism among some scientists, yes. The challenges, especially around scaling up while controlling errors, are immense. But the progress continues to be rapid, and people are developing benchmarks to try and compare these different machines fairly.
Okay, now let's pivot to that connection we mentioned earlier, quantum computing and AI. Quantum AI, what's the big idea there?
Quantum AI is this really exciting, emerging field looking at how these two powerful technologies can work together. The core idea is that quantum computers might be able to accelerate specific, really computationally heavy parts of AI algorithms.
Which parts?
Things like complex optimization problems that crop up everywhere in AI, or tasks involving sampling from really large, complex probability distributions, or processing data that has a huge number of features, high-dimensional data.
So the quantum computer acts like a specialized coprocessor, a booster engine for the tough bits of AI.
That's a great way to put it. A lot of research focuses on hybrid quantum classical architectures. The classical computer does most of the work, but hands off the really hard computational kernels to the quantum processor.
Makes sense. Leverage the strengths of both.
Exactly. Another angle is using data generated by quantum systems to train AI models. This quantum data might have unique statistical properties that could lead to better AI models, perhaps faster training, needing less data, or achieving higher accuracy.
Interesting. Can you give examples in specific machine learning areas, like, say, supervised learning?
Sure. In supervised learning, where you train a model on labeled examples, quantum algorithms might speed up the optimization part of training. Finding the best settings for models like support vector machines or even linear regression could potentially be done much faster. There's work on fault-tolerant quantum ML aiming for big speedups, and also near-term NISQ approaches trying to get some advantage with today's noisy machines.
What about unsupervised learning? Finding patterns in unlabeled data.
Quantum annealing, which we talked about for optimization, could be useful there for tasks like clustering data points or image segmentation. And people are developing quantum generative models, things like quantum Boltzmann machines or quantum GANs, which could potentially generate more realistic or diverse synthetic data for training other AI models.
Quantum GANs, wow. And reinforcement learning.
That's also an active research area, exploring if quantum approaches can help AI agents learn optimal strategies more effectively in complex environments.
So it seems quantum could potentially enhance many parts of the AI toolkit. Is it a one-way street? Or can AI help quantum computing too?
Oh, it's definitely a two-way street. AI and machine learning are proving really valuable for quantum research itself.
How so?
Well, quantum experiments generate tons of complex data. AI can help analyze that data, find patterns, maybe even help optimize the experiments or the design of quantum hardware. A big area is using AI to help tackle quantum error correction or mitigation learning noise patterns, devising better correction strategies. AI can even help design better quantum algorithms or circuits.
That's a fascinating synergy.
Yeah.
Each field pushing the other forward. What about that black box problem in AI, the interpretability issue? Can quantum help there?
That's a really intriguing possibility. Many complex AI models are hard to understand. Why did it make that decision? It's a big issue for trust and safety.
Right.
Some researchers think that because quantum systems process information fundamentally differently, perhaps quantum AI models or models trained on quantum data might be inherently more interpretable. Or maybe quantum approaches could help us probe and understand classical AI models better. There's work on concepts like GenQI exploring this. And AI is also being used to help design quantum circuits that are easier for humans to understand, like with the GQE methodology.
Building AI we can actually understand and trust, that would be a massive win. Are businesses taking notice of quantum AI?
They definitely are. Surveys show a growing number of companies are either investing in or actively exploring quantum AI. They see the potential. Big players are partnering with quantum hardware companies like IBM, D-Wave, Quera.
But they must have concerns too.
Oh, absolutely. The main ones are usually cost, the current lack of clear, near-term applications with proven ROI, and just a general lack of deep understanding of the technology within their organizations. It's still early days for practical business use cases.
Understandable. It's high risk, high reward territory right now. I also saw a mention of quantum associative memories. What's that in the AI context?
Right, those are a type of quantum neural network. The idea is they could be much better at pattern recognition than classical associative memories. They might be able to store many more patterns and recall them more effectively, even if the input is noisy or incomplete, could lead to much more robust pattern matching in AI down the line.
And then there's the idea of fully quantum machine learning. Everything quantum.
That's sort of the ultimate vision for some researchers, yeah.
Right.
Where the data representation, the processing, the learning model itself, everything operates according to quantum rules. We're quite far from that, but it's a direction people are thinking about.
Okay, this paints a picture of incredible potential, but also a long road ahead with significant challenges. What's the big picture view looking forward?
I think the key takeaway is that realizing the promise of quantum computing, and especially quantum AI, needs sustained effort and collaboration. We need quantum physicists, computer scientists, AI researchers, engineers, all working together.
And breaking down silos.
Exactly. There are still fundamental questions to answer about how quantum mechanics and machine learning really interact. We need open source tools, standardized ways to measure progress benchmarks, and strong research communities. We need more AI experts getting involved in quantum and better software tools to make it easier. And of course, continued funding and education are crucial.
So let's try to wrap this up. We started with the basics of computing, classical bits, and their limitations. Then we dove into the quantum world, qubits, superposition, entanglement, this whole different way of processing information.
Right, harnessing quantum mechanics itself.
We touched on the history, back to Feynman's vision, explored the different ways people are trying to build these machines, annealing adiabatic gate-based photons.
The whole zoo of approaches.
And the huge potential impact cracking encryption, yes, but also revolutionizing medicine, materials, science, finance, logistics, solving problems currently impossible.
Problems limited by that exponential scaling on classical machines.
But we also looked at the reality today, the NISQ era, the challenges of noise, decoherence, the massive hurdle of error correction, and the quest for stable logical qubits.
It's a marathon, not a sprint.
And finally, this exciting fusion with AI, quantum AI, using quantum to boost AI, using AI to help build quantum computers, maybe even leading to more interpretable AI. It's clear that while having a quantum computer on every desk is still a way off,
Well, a long way off, probably.
the research, the investment, the sheer brainpower being poured into this is accelerating incredibly fast.
Absolutely. The convergence of quantum computing and AI, it really feels like we're on the cusp of something potentially transformative.
It really does. So as we close out this deep dive, here's something to think about. Given how quantum computing could shake up not just tech, but science, security, maybe even our fundamental understanding, what are the truly unexpected things? The discoveries or disruptions we haven't even conceived of yet. It feels like a genuine leap, and pondering those long-term ripples is, well, pretty mind-bending. Thanks for joining us on the Deep Dive.